Complex and rational zeros of a polynomial. The first theorem says if you have a plus bi is a 0, then you're going to have a minus bi as a 0. So if you have one complex number, you're automatically going to have its conjugate. The conjugate, once again, is the same as the original. You just switch the sign in between. So for this problem, same as the Jeopardy problem we've been looking at the last couple of days. We know it's degree 4. We're told are 2 zeros. But you'll notice that since this is a complex number, the theorem we just talked about says we're going to automatically have its conjugate. We know when we're dealing with a Jeopardy, we always set x equal to our original 0. So we're going to set x equals to 3 plus 5i. But that theorem we just looked at said we also need to include its conjugate. So we have 3 minus 5i. Then we have our second 0 that they gave us. And that's also a complex number. So we got to also have our other possibility of its conjugate. And each one of these, remember in working backwards, you always want to get 0 on one side. So here we're going to have to subtract a 3 from both sides, subtract a 5i from both sides. Here we got to subtract a 3 from both sides to get 0 and add a 5i to both sides. On this one, we'll have to add a 1 and add an I to both sides. The one on the right here, we'll have to add a 1 and then subtract I. Now remember, it's those things that are set equal to 0 that you end up putting in your function for the factors that you multiply together. So we're going to multiply all 4 of these together, and that ends up being our function. Now, you'll notice we have lots of i's hanging around. We don't want i's left in our problem. What you want to do is you want to go ahead and multiply the 2 green parentheses together. Those are the ones that contain the conjugates. When you do that, your i's will drop out. You'll want to multiply the 2 gray ones together. And if you do that correctly, your i's will drop out. So in other words, to eliminate some of your i's, you multiply the 2 factors that have the conjugates in them, and the i's will disappear. When you go ahead and multiply out the 2 green parentheses, taking your x here times all 3 of these, taking your negative 3 times all 3 of these, taking your negative 5 times all 3 of these, you end up getting an x squared plus 6x plus 34 when you combine all your like terms. When you multiply the last 2 gray parentheses together, you get an x squared minus a 2x plus a 2. This theorem says if your function has any rational zeros, meaning those that could be written as a fraction, they're going to be in this form here. A factor of a constant over the factor of your leading coefficient. Well, when we look at this particular problem, we want to go ahead and list out all the possible rational zeros. Your constant is the one that has no variables in it. So you look at the factors of your negative 2. Plus and minus 1, plus and minus 2. Those are the factors of your constant. Then we've got to put those over the factors of your leading coefficient. Your leading coefficient is the one that's in number in front of your term with the highest exponent. So you're going to have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. Those are the factors of your leading coefficient. We now need to list out all these different possibilities. So you got to take each one of these up here and pair them up with each one of these down here. So you could have 1 over 1, which is 1. You could have 1 over your negative 1, which is negative 1. Take your 1 over your 2, your 1 over your negative 2, your 1 over your 3, your 1 over your negative 3. your 1 over your 4, your 1 over your negative 4, your 1 over your 6, your 1 over your negative 6, and you keep listing them all. Then you got to take your 1 over your 12 and your 1 over your negative 12. Then you'd have to come back and do the negative 1, but negative 1 over any of these is just going to repeat what we have. Then you got to come back and put your 2 over each one of these down here. So you could have a 2 over your 1, 2 over your negative 1. 2 over 2, that's already listed as your 1. Or you could have your 2 over your 3, plus or minus 2/3. Or you could have your 2 over your 4, but that's a half and already listed. Or you could have your 2 over your 6, which is a third but already listed. Or you could have your 2 over your 12, which is your 1/6, which is already listed. So here's all your possible rational zeros. Now we want to find the zeros of this function. After we find our possible rational zeros, we want to go ahead and find our m. Remember, m is your largest coefficient or constant, which is 12, over your leading coefficient, which is also 12. So it'd be 12 over 12, which is 1, but then you got to always add 1, which is 2. So that means when you are looking at m, all your x's or your roots will occur between -2 and +2. So your x-min is -2, your x-max is +2. We then want to go ahead and graph this to see what is likely to work. Well, we're going to graph from a -2 to a +2. That's what we just figured out for our m. We just want to be right above the axes and right below your axes, so that's why I have it as -1 to 1. You graph that, and we get this. And while with this being -2, -1, 1, and 2, we can say, okay, where does it appear to be crossing? Well, it appears to be crossing here at a half. It also appears to be crossing at -1/2 and at -2/3. So those are the zeros that we're going to go ahead and try. So, and they're all from our list of possible rational zeros. So I'm going to try 1/2 doing synthetic division. And it works. That's good. So we know 1/2 is a factor. When you look at your quotient, we get this. That just comes from right here. So one of our zeros is a half. Our other zeros, since it's quadratic, we could just go ahead and solve this quadratic equation. Well, to simplify it, we could divide everything by 2. We had to have smaller numbers. It's not going to factor nicely, so all we have to do is use our quadratic formula. Opposite of b plus or minus b squared minus 4 times a times c over 2 times a. So we simplify the root. We get -7 plus or minus, and our root simplifies down to 1. We then can write it as two separate problems, a -7 plus 1 over 12. So we get -1/2. And that was one that we suspected, but we actually had to show that it did work. And then we're going to go ahead and go the -7 minus 1 over the 12, and that gives us our -2/3, and that's the other one we suspected. So our zeros then are the 1/2 that we tried in synthetic, the -1/2 that we got out, and our -2/3 that we got out. Those are our zeros.